Okay, so today we're going over action potential. And action potential, this is the graphical representation of what occurs during action potential. And action potential is really a positive feedback mechanism. First, we have our resting potential, which is what the neuron is usually at. The resting potential is normally at between negative 60 and negative 70 millivolts. So the resting potential is the difference between the inside of the electrical potential and the outside of the electrical potential on an ion. It's found with the voltmeter. So if you were to get a voltmeter and put maybe here, right, this is your voltmeter, you subtract the inside with the outside, that's how you get your negative resting potential. So the action potential occurs once the electrical impulse reaches the threshold value. This is known as the all or nothing law because it either reaches the threshold value and then it stimulates the action potential or it doesn't at all. Right above the threshold value, you have what's occurring is depolarization, meaning the inside of the cell membrane is it's less positive than the outside. And what's happening here is that you have all the voltage-gated sodium channels opening up, and that's allowing an influx of sodium ions to go into the cell membrane, into the axon of the neuron. And then once it reaches about 30 millivolts, you have something called repolarization occurring, which is when all your voltage-gated so in repolarization, you have your voltage-gated sodium channels closed tightly, and then that stimulates the opening of the voltage-gated potassium channels, which once it opens, it allows potassium to leave the cell, and what that ends up causing is the inside of the cell to become less positive than the outside, so it brings it back to normal. And then it will dip down beyond the resting potential for a short period of time before increasing. This is where the NAK pumps start functioning again, and then that would maintain its resting potential. So this is a zoomed in portion of the nodes of Ranvier, which is between the gaps between the Schwann cells. And here in this membrane, that's when you have all these transmembrane proteins. And this is, I divided the regions up. This is the resting region, so this is where your resting potential is. And normally what occurs is you have a less positive membrane compared to the outside. So this is, structure is a zoomed in portion of the nodes of Ranvier, which is between the Schwann cells. And then on the cell surface membrane of this diagram, you have 4 different types of transmembrane proteins, and all work to form the action potential. So in this region, you have the resting region, which is your resting potential, and here inside the membrane is less positive compared to the outside, which is more positive. So here you have the sodium potassium pump producing and maintaining the gradient. Mm-hmm. You have lots of potassium ions here being pumped into it, and then being pumped outside of the axon is the sodium ions. So this resting region is maintained not only by the NAK pump, but also by the leaky potassium ion channels. So when this becomes too concentrated in potassium, the potassium will diffuse out, and then the NAK pump will keep working. But in an action potential, when it reaches at the threshold value, you have depolarization going on, which is when the sodium voltage-gated channel is open, sending in more sodium ions, along with the potassium ions that are already in here. And what that creates is a local circuit, meaning that all these positive ions are repelled against each other. Mm-hmm. Meaning they won't go back to the resting region, they flow one way down the cell membrane. It flows down the cells rather than the cell membrane. So basically depolarization causes a local circuit, and this is where the positive feedback mechanism comes in. And then, as these ions move to an area where they're not being rushed in, the same reaction or the same action potential would occur in an adjacent region. So that is basically, that's action potential. The only difference is like within action potentials, you cannot have different action potentials merged together. Meaning this whole action potential is a refractory period. So that's why the impulses never go back, because at this moment and after this occurs, it's trying to go back to the resting potential.